Welcome to our presentation for the AI and visualization, the assignment 2. In this assignment, we have covered clip and cross attention maps from text to image generation process. So we will reveal the internal mechanism and we will explain how to use clip to detect the context of an image. So let's proceed. So first we will explain the clip embeddings and cosine similarity. So how it works. So the computer vision model like ResNet only understand the pixel patterns. So they could classify a dog, but did not understand the semantic concept of a loyal four-legged pet. So it cannot understand the semantic concept for our visual meaning or understanding. So the clip is contrastive language image pre-training maps both images and text into a shared vector space. So this allows the model to understand images through the lens of a natural language. So what's that? Here we have text encoder and an image encoder. So a transformer that converts text prompt into a vector, an image encoder, a vision transformer that converts pixel data into a vector. So here we can see it's visually. So the system is trained so that the vector for a dog is geometrically close to the vector of an image of a dog. The mathematical model of embeddings and cosine similarity mapping to latent space. So an embedding is a mapping function that takes a high dimensional input like pixels and outputs a dense vector. So in clip we project both modalities to a normalized hypersphere as we can see. The cosine similarity, the dot products. Since our vectors are normalized to length 1, the cosine similarity is simply the dot product. So it measures the cosine of an angle between the two vectors. So if they are in same direction, their angle is 0. So for opposite direction, they are orthogonal. So their angle will be 90 degree. So here we can see the explanation. So if two vectors point in the same direction, they share the same meaning. The model's goal is to rotate the image vector until it aligns with the text vector. So we have run it in code. So first we have imported all the libraries, the clip tokenizers and the clip vision transformers. Then we have we have added the text embedding. Like we have uh, inserted 4 images here: a dog, a dragon, a tiger, and a cat. And here we have the text embeddings, and here we have the images we have printed here. All are AI generated images. And then in this code, we have printed the embedding with clip image text similarity heat map. So this is the similarity heat map where from the image for a dog, it created 0.26. So this is the maximum. For a dragon, it's 0.28. For a tiger, it's 0.31. For a cat, it's 0.26. So is it statistically significant? In high dimensional space, like 512 dimensions, random vectors are almost always orthogonal. So, like for a dog, a score of 0.26 indicates a clear semantic signal. While not a perfect match, it suggests the model sees a strong relationship between the prompt and the image compared to background noise. So, this is the highest relationship score in this case. So, how the text and image embeddings works in Clip. So, next, this is just a learning process, how actually the internal mechanism works. Now we are explaining a very interesting finding that we will detect visually similar but in different contexts with clip. So, as what is the abstract ambiguity? A single prompt like safe is abstract. Does it mean a safe box, a safe driver? The model's latent space representation of a single word is broad and fuzzy. So, what does a safe mean? Only the word. It doesn't have any semantic meaning or any contextual clarity. So, when we use a concrete description in clip by a dense list like physical barriers, relaxed body, we can grab the semantic meaning with clip. First, we have to produce a softmax distribution and a description in clip. So the list of description like what should be the criteria to detect the cute or ugly. Like we have developed the description a cute, adorable, lovely image, and for the ugly and ugly, scary, distinguishing image, disgusting image. So here we have separated these positive versus negative words in the embedding space separated with comma. So this is a list, this is a vector, and we have separated both positive and negative descriptions with a comma. And here we have determined by a softmax. So in here we have indicated that the positive word should be in right direction and the negative should be in left direction. So if it's greater than zero point 0.5, the softmax value, then it should be in positive direction. And for the negative value, it should be in left direction. So in this case, we can see the dog, I mean the puppy is very cute. So our predictor predicted is it as a very cute and the prediction score is 0.98. So it's close to 100%. So with this description, the clip could predict with a very high confidence score. We can see the confidence score is nearly 4. So the negative prediction and the positive prediction difference is pretty high in clip. So based on this criteria, we have developed some safe and dangerous understanding from a visual image. Like for a safe, dangerous, we have created these token words to understand the context like secure place, physical barrier, supervised area, safety rules, calm behavior, non-aggressive, and for the dangerous like unsecured place, no barrier, aggressive animal, threat display, gun violence, teeth visible, wild nature. So with this kind of words, we can detect the semantic meaning with clip from an image. So this is the mathematical formula of cosine similarity as we have described before also. And this is the working mechanism of our softmax. So we convert the raw cosine similarities into probabilities using softmax for a safe versus dangerous. So safe is a scale similarity between the image and the entire safe list. So for the danger is a scale similarity between the image and the entire danger list. So this is the probability like epsilon, the exponential of the safe list by the exponential of safe list plus exponential of the danger list. Now we can actually understand clearly. We can see a tiger is caged inside a zoo and two visitors are watching from a safe distance. So as we mentioned in the clip description, the physical barriers, contained safe, relaxed body. So with these embedding words, from this image, a tiger is detecting as safe by our softmax predictor. Normally, a tiger is considered as a very dangerous animal. But as we have explained in clip with the words, like here, a secure place, a physical barrier, calm behavior, relaxed body, non-aggressive. So as these words are matching from the visual properties of the image, that's why the tiger is being detected as safe by clip. So we have clarified with our text embeddings to clip model. That's why it can understand the whole context in this image or the situation. And also when a tiger is attacking in wild and it's being detected as dangerous. So the detected features we have added in the text embeddings, the aggressive animal, the teeth visible, wild nature. So with these text tokens, the clip could capture the semantic understanding in this image that the tiger is dangerous in this context. So that's how the clip model can differentiate the visually similar but different contexts and the behavior of an object. So this is the pipeline like list 5 we define the dense keywords, then we are creating the encoding super vectors, then the image embedding, then the comparison of cosine similarity, and the final is the binary softmax. So using ensemble embeddings of detailed description allows clip to detect nonce attributes that single word prompts miss. And at this stage, we are revealing the internal black box of the text to image generation, the cross attention map. So we have produced the image using Comfy UI. So here we have connected the blocks. As we can see, this is our prompt. So we are using the stable diffusion model, which is very old model. So we have to clarify a lot of positive prompts and negative prompts to create detailing, but still the image quality is not so high as we can see the latest models like Gemini, Nano Banana can generate very highly detailed images. But actually, the attention maps visualization needed a lot of hard coding, which is added with the custom node, the attention map nodes. So by these nodes, it can take the input from these blocks and can reveal the internal cross attention maps. So I am going to explain this in the next slides. So here is the prompt and is the generated image. We have used Edward Robert Hobbes art style. So the self attention map. So we have used the model stable diffusion 1.5 with 100 steps and the guidance scale was 10 and the workflow is from input states, so it converts text encoding and noisy latent image. Then the attention mechanism, the query key matching, attention weighting, the output stage, the feature map and denoising. So in the input stage, when we are applying the text from, it's converting the noise into latent space and the tokenization and encoding. Like the prompt is broken into tokens and converted into numerical vectors that captures semantic meaning, like the Ophelia in a moonlit. So it converts the prompt into keywords as a vector. Then the random noise, as we have generated 512 pixels. So the same size of a random noise canvas is generated. So the image is compressed in the latent space. Then both streams are formatted to the attention mechanism, the token and the image. So this is the attention mechanism we can see. The attention mechanism mathematical formula is the Q, K and V, the softmax. Q into K to the power T by square root of dk into V. So what is the query matching? For each image feature in the pixel region, the model calculates how much it relates to each text token. This is the dot product between query image and the key text. So this one, the attention weighting. The scores are normalized via softmax to create probability distributions. High values in red indicate strong relationships like Ophelia, high weight, on face upper body, flowing, high weight on hair water region. So the artist shines a flashlight on a specific canvas area while hearing each word. The heat map shows exactly where the flashlight points for each word. So the output states it context aware features. The attention weights multiply the value vectors in the semantic content of text tokens. This creates image features that explicitly incorporate textual guidance. Then the denoising, the unit denoising and refinement. The unit uses these features to strategically remove noise. So the like flowers token enhances detail in a specific region. Flowing token creates fluid textures in water or hair, and the final image generates. So in the self-attention map, we have visualized basically in five stages like the course structure, the large faint blobs define major element locations. The composition solidifies. Central shapes lock, like Ophelia focuses on face and body, like the main object, the main character, face and body. The detail emergence, so multiple small points appear for flowers and features. The texture refinement, patterns emerge for hair, flow, and water ripples. And the final touches, like sharp, highly localized focus for crisp rendering. So we can see at which positions the map is focusing, the position of the images, different positions. As we can see, the central shape locks in focus on face body. So maybe this is the place of the face body and some regions of hands. Also, we can see the patterns of hair flow and waters. The main mechanism is the cross attention mechanism. So we can visualize the detailed step by step. So where how the text embeddings focused on the canvas on different locations of the canvas. So it's the same like the token embeddings. And I have also explained the mathematical model of the attention mechanism. So like if we check the token and the semantic vectors, the tokenization process, the prompt is split into meaningful units with clip tokenizer. The embedding each token converted into 768 dimensional vectors. The projection, the two separate learned transformations create key and value vectors. Like a key inside, the Edward and Hobbes have similar vectors because they are strongly associated in them. So from this key inside, Philip understood that this is the name of a single person and it has a art style. The projection mechanism, the keys K, what to match, and the values, what to apply. And it decodes the noisy latent to the queries, like what's happening, noisy latent, current denoising state. It's 64 into 64 into 4 dimension in latent space. The feature extraction, the unit encoder extracts multi-scale contextual features from noisy input. Then the query projection. Features are transformed to query space via learned projection matrix WQ. Spatial questions. Each spatial positions becomes a query asking which text token is most relevant here. The key insight. Queries from here region will naturally have higher mathematical compatibility with flowing and hair tokens. That's how the compatibility scores, the attention weights, and the contextual injection works. The similarity matrix, the dot product of Q and K to the power T. This raw measures dictates relevance between image region and text tokens. The normalization, the A. Softmax scales the raw scores to each image position, distributes its attention across all text tokens, creating the attention map. The semantic injection, the weighted map A combines the text value vectors, resulting in embedded enhanced image features that are now guided by the prompt. And the final output. These enhanced features are returned to the unit block to guide the next denoising step. So we can see the cross attention mechanism, that how the different regions are being focused and the details are created step by step in the image. So from the prompt to this image generation, all these steps are followed. So this is revealed by the cross attention maps. Also we can see different prompts and the image and their visualization. Here we have used to generate different artist styles. Like in this image we can see Albrecht Dürer's painting style and the self attention map and the cross attention maps. And here the Leonardo da Vinci's painting style. So thank you very much. I hope I was able to explain the mechanism clearly.